Today, we're going to pull back the curtain on something pretty ambitious in live video engineering. We're talking about building an always-on pipeline, not just reliable, but one that stretches across multiple clouds. Think about that challenge for a second. Massive traffic needs to be super resilient and, get this, deliver content with basically no delay. We mean less than a blink of an eye, sub 100 milliseconds from the source right to your screen. So how on earth do you even start designing something like that?
Yeah, that's exactly the beast we're tackling in this deep dive. And, for anyone prepping for those senior DevOps or cloud interviews, this is gold. It's precisely the kind of complex, real-world problem solving you'll need to demonstrate. So our mission today is really to unpack the design of a multi-cloud active video processing pipeline. We'll look at tools like AWS Elemental MediaLive and Azure Media Services, and specifically how they hit that crazy fast sub 100 millisecond latency target. But the real core, the absolute linchpin we need to understand, is how the systems state the live information about the stream gets synchronized perfectly across these different clouds. That's what makes it all hang together.
Right. And the source material we're digging into here, it's really practical, very technically sharp, structured, almost like you'd expect in a top-tier technical interview setting. It's just packed with insights if you want to get your head around this kind of cutting-edge cloud stuff. Makes some really complex ideas, well, pretty digestible. No, okay. So let's start peeling back the layers. When we say active multi-cloud video processing pipeline, what does that actually mean in simple terms? And why is hitting that ultra-low latency, that sub 100 millisecond goal, such a difficult, demanding thing to achieve? Sounds like we're right at the edge of what's even possible.
You're absolutely right. It is pushing the boundary. So maybe the quick version first. An active multi-cloud pipeline basically means you've got two or maybe more completely separate, fully working video processing systems running at the same time. In different clouds like AWS and Azure, they're both actively handling the exact same live video stream. That active part gives you extreme resilience, like failover is almost instant. And the ultra-low latency, that just means the whole trip, camera to viewer, happens faster than you can blink.
Okay. Faster than a blink. Wow.
Yeah.
So how does the overall design look then, in more detail?
Right. The detailed picture, the overall design, involves setting up identical active systems on both AWS Elemental MediaLive and Azure Media Services at the same time. The key idea is that both clouds are taking in the exact same source feed, usually through edge endpoints that are geographically close to the source, just to cut down that initial network delay.
Makes sense.
Right.
Minimize that first hop.
Exactly. And a really fundamental choice here is building everything with stateless microservices. This means every single step, ingest, encoding, packaging, sending it to the origin servers, is broken down into these small independent services. And critically, they don't hold on to any specific session data themselves.
Stateless. So they don't remember anything about the stream passing through them.
Precisely. And the genius of that here is that if one little service fails, it's not a catastrophe, it's just a blip. Another identical service just picks up the slack instantly. It makes the whole system kind of anti-fragile, resilient by design. And it also makes failover super smooth and scaling really easy and symmetrical across both clouds.
Okay, stateless is key for resilience and scale. What about hitting that speed target, the sub 100 milliseconds?
Ah, right, that ultra-low latency part. Getting consistently below 100 meters end-to-end, that takes some specific tech. We're talking about using things like CMAF-LL, that's Common Media Application Format with low latency, or maybe even WebRTC in some cases. These are basically hyper-optimized ways to chop up and deliver video almost instantly. The strategy involves minimal segment packaging, breaking the stream into tiny, tiny pieces.
How tiny are we talking?
Really tiny. We often aim for segment lengths of 1 second, maybe even less. You reduce the group of pictures, the GOP length way down. Shorter GOPs mean faster updates. You also have to be really aggressive about cutting down or even disabling the player's startup buffer. Any buffering adds delay, even milliseconds count here. And finally, you need low latency TCP tuning right at the network edge, optimizing how data packets are sent to shave off every possible millisecond of network delay.
Okay, so a lot going on just to get the basics working fast and resiliently.
Definitely. So maybe to quickly recap the core ideas for this part. 1, active redundancy, identical systems running live in multiple clouds. 2, stateless microservices, that's your key to failover and scaling. 3, ultra-low latency tech, things like CMAF-LL, WebRTC, tiny segments. And 4, aggressive tuning. Both the player buffer and the network itself need optimization.
Right, that sets the stage really well. But now, the big question you hinted at earlier, you've got these two independent systems, AWS and Azure, running in parallel, both active. How on earth do you keep their state, what they know about the stream, perfectly in sync? Especially when, like you said, every millisecond matters for that seamless failover. This sounds like the really tricky part.
It absolutely is. This is the heart of the problem, the synchronization challenge. So the short answer, the secret sauce. It's using a special kind of database, a conflict-free, multi-master distributed database. This database instantly shares every single change between the clouds using something called change data capture, or CDC, and often it uses clever data types called CRDTs to handle situations where both clouds try to update the same thing at once.
Okay, a special database, CDC CRDTs.
Hmm.
Let's unpack that. What exactly is state in this video context?
Good question. State here covers all the critical info both clouds need to agree on. Things like stream session metadata, the basic info about each live stream, the health status of the live input feed, the current settings for transcoding the video, the status of the manifest file, which tells the player how to assemble the stream, and any dynamic rules for controlling users or traffic flow. All that needs to be identical on both sides.
Got it. So how does this special database approach work?
The core is that conflict-free, multi-matter distributed database. Think systems like DynamoDB Global Tables on AWS, or Cosmos DB multi-region on Azure, or maybe even something like Redis Enterprise Active. These are essential because they let both clouds read and write state data simultaneously from anywhere, and the database itself figures out how to keep everything consistent. The conflict-free part is crucial. It means if AWS and Azure both update, say, a stream setting at almost the exact same time, the database has built-in rules to resolve that without causing errors or losing data.
Okay, so the database handles potential conflicts. How do the changes get shared so fast? You mentioned CVC.
Exactly. Change data capture, CDC agents. These are like little listeners attached to the database. The moment any state data changes, a stream starts, an error pops up, a setting is tweaked, the CDC agent grabs that change and pushes it out to the other cloud's database almost instantly. We're talking replication times, often in the 10 to 50 millisecond range. Super fast. This minimizes how long the two clouds might be out of sync.
And the CRDTs, what do they do?
CRDTs, conflict-free replicated data types. These are, well, they're like a mathematical way to structure data so that conflicts just resolve themselves predictably. Think of them like smart data structures. Even if updates arrive out of order or happen concurrently across clouds, CLCTs guarantee that both sides will eventually reach the exact same final state. They often use rules like last writer wins, or maybe something more complex like merge by vector clock to ensure consistency without needing complex locking mechanisms, especially during high traffic or failover events. They really simplify building these kinds of multi-active systems.
That's fascinating. So it's like they inherently know how to merge updates correctly.
Precisely. Maybe an analogy helps. Imagine you have two live TV studios, one is AWS, one is Azure. Both are broadcasting the same live event. Instead of just relying on one, they both stay perfectly in sync by constantly updating this shared magic whiteboard that's our distributed state database with every single change. Camera angle change, write it down. Technical glitch, write it down instantly. So if one studio suddenly goes dark or lags behind, the viewers don't notice anything because the other studio has the exact same up to the millisecond script.
That's a great analogy. So the components map like.
Yeah, so in that analogy, the ultra-low latency encoders and packagers are like the tech crews, slicing the feed into tiny bits and getting it out super fast. The state synchronization bus powered by the database and CDC is like a digital walkie-talkie system, instantly telling both studios every single update. And the multi-CDN delivery and smart routing, that's like the network of broadcast towers and the traffic controllers automatically switching viewers to the best signal if one tower has issues.
Okay, and a quick practical example, like a camera change.
Sure, a camera angle changes. Both AWS and Azure immediately see that state change via CDC. They update their internal processing workflows. They generate identical stream manifests reflecting the new angle. For you, the viewer, it's just a seamless cut. No black frames, no glitches, no repeated footage. Just a smooth transition, even though two separate systems coordinated it across different clouds.
Wow. Okay, so the key takeaways from this synchronization piece would be?
Right. 1. You absolutely need that distributed database multi-master, conflict-free as the core. 2, instant propagation using CDC is vital for that sub-100 meters failover target. Changes have to move fast. 3, Conflict resolution, often built in using CRDTs, is essential to handle simultaneous updates without breaking things. And 4, think of it like those synchronized studios. Constant communication is key to seamless redundancy.
That analogy really lands it. So, okay, we see the complexity, we see how it works, but why go through all this? Why is this specific active, multi-cloud, super synced approach considered, the top tier compared to simpler ways to build resilient video pipelines? What's the big payoff?
That's a fair question. The justification is really about achieving a level of resilience and performance that other methods just can't match. And that translates directly to business value, so the short version. It gives you unmatched resilience, basically zero failover time, and massive scalability. For live events, that means no drop viewers, no lost revenue, just a flawless experience. Simpler active-passive or single cloud setups just can't guarantee that.
Okay, so resilience and near zero failover time are the big drivers. Can you elaborate on why this design enables that so well?
Sure. That stateless video pipeline design we talked about, it's a huge factor. It allows for really fine-grained failover. If one single encoder microservice has a problem, only that tiny part is affected. Another one takes over instantly. It's not like the whole system grinds to a halt. For a business running a major live event, this is critical. It means uninterrupted streams, which means protected revenue and, frankly, protected reputation. An outage, even brief, can be disastrous. Plus, this stateless design means you can easily scale out horizontally. Need more capacity? Just spin up more microservices across both clouds. And load balancing becomes much simpler because there's no single bottleneck.
And the multi-master sync plays into the speed of that failover.
Absolutely. That multi-master replication is what makes sub 100 millisecond failover achievable. Because both clouds are constantly writing and reading updates bidirectionally, they always have the current state. When a failure happens, the other side is already running, already has the latest information. There's no delay waiting for a passive system to spin up or catch up. Active passive systems, they'd have a noticeable delay during failover, maybe seconds, maybe longer. In ultra-low latency scenarios, that's unacceptable. This symmetric, always-on approach eliminates that.
Got it. So key reasons for this approach are?
I'd say 1, business continuity. It protects revenue and reputation during high-stakes live events. 2, granular failover. Stateless design means tiny failures don't cause big outages. 3, symmetric scalability. Handle huge audiences easily across both clouds. And 4, near zero failover time. That multi-master sync makes transitions practically invisible to the viewer.
That makes a very strong case. But it sounds incredibly complex, like walking a tightrope. There have to be pitfalls, right? Those production gotchas, the things that look fine on paper but can bite you when it's running live with real traffic. What are the big things to watch out for?
Oh, absolutely. It's definitely a high-wire act. Even with perfect design, things can go sideways in production. Quick summary of the danger zones. Subtle network problems, CDNs not tuned right, clocks drifting between clouds, and the failover process itself not being fast enough. Any of these can ruin the magic.
Okay, let's hear the details on those gotchas.
Right. First, network jitter and packet loss. Even tiny inconsistencies in packet arrival times or lost packets between the clouds or out to the CDN can cause visible glitches or add latency. It breaks that seamless illusion. You absolutely must have network observability tools running in every single VPC and subnet, constantly watching for segment drift and latency spikes. You need deep visibility.
So network monitoring has to be obsessive. What else?
Second, CDN and player edge tuning. We talked about minimal player buffers. You have to enforce that. Any significant buffering kills your low latency goal. And reducing that segment or GOP length down to a second or less, that needs careful tuning across your entire media stack and across all your CDNs. It's not just a server-side setting.
Right, the whole chain needs to be tuned.
Exactly. Third, cross-platform drift. This one's sneaky but critical. You need absolutely strict global time synchronization, usually using NTP, Network Time Protocol, or even GPS clocks on all your servers in both clouds. If the clocks drift even by a few milliseconds between your AWS nodes and your Azure nodes, the video segments won't line up correctly at the player. It causes weird playback issues. A good trick for debugging this is using timecode burn-in directly onto the video frames. It helps you visually see if the playhead latency matches the source time, pinpointing where drift is happening.
Time sync is crucial.
Right.
Okay, what's the last big one?
Fourth, The failover choreography. The whole process of detecting a problem in one cloud and switching traffic or sessions to the other cloud has to be lightning fast. Those cross-cloud health checks and the logic to resume a session on the other side, that whole sequence needs to complete in under 50 milliseconds. Any longer, and the end-to-end service might hiccup, potentially causing a viewer visible glitch despite the active setup. It needs to be automated and incredibly quick.
Under 50 milliseconds for the failover decision and execution. Wow.
Yeah, it's demanding.
Mm.
So key gotchas to really focus on. 1, network vigilance, monitor jitter and loss obsessively. 2, player and CDN optimization, no buffers, tiny segments everywhere. 3, global time sync, non-negotiable, use NTP GPS strictly. And 4, rapid failover orchestration, automate it, make it sub 50 meters fast.
That's a really helpful, if slightly terrifying, list of warnings. Okay, we've looked at the pieces, the benefit, the risks. Let's try to zoom out now, put it all together. What does the complete architecture look like visually, conceptually? And what are the fundamental trade-offs you're making with each major part of the system?
Okay, let's paint that bigger picture. And yeah, every single choice here involves trade-offs. There's no free lunch. So the quick architectural overview. You've got parallel processing pipelines in each cloud, active. State is kept in sync using that multi-master database with CDC. Video is chopped into ultra-small segments for low latency. And delivery happens through 2 or more CDNs with smart switching. Each piece gives you something great, like resilience or speed, but usually costs you in complexity or operational overhead.
Right. Can you break down those trade-offs component by component?
Sure. Let's look at the main ones. 1,
Yeah.
active processing itself.
Yeah.
Strength, unbeatable resilience, lowest possible failover time. Trade-off. It's complex to set up and manage, and you're essentially paying double for infrastructure because everything's duplicated. It's expensive.
Cost versus resilience. Classic trade-off.
Yeah. Exactly. 2, multi-master CDC state sync. Strength. Enables that near-instant failover, keeps both sides perfectly up to date with bidirectional updates. Trade-off. You can run into tricky event ordering issues under extreme load, and you absolutely need solid logic to handle potential split-brain scenarios where the 2 clouds might momentarily disagree on the state before the sync catches up. That needs careful design.
Sync power versus complexity and potential edge cases. Okay.
3, ultra-low latency segmentation. Strength. Near real-time viewing enables real interactivity like betting or polling during a live stream. Trade-off, it can shrink your error correction window. With such tiny segments, there's less buffer or time for the system to recover from a network glitch or a processing hiccup before the viewer sees it. It makes the stream more fragile in some ways.
Feed versus robustness against network noise.
Makes sense. And 4, dual or multi-CDN egress. Strength. Content is always available from somewhere. You get better global performance routing viewers to the closest CDN edge, and it's great insurance if one CDN provider has a major outage. Trade-off. More monitoring complexity, managing multiple CDNs, more complex configuration, and usually higher data egress costs.
Availability versus management overhead and cost.
Got it. So summarizing those trade-offs, active, resilience plus versus cost complexity plus exit, multi-master sync, failover speed plus sync complexity split brain handling, low latency segments, interactivity plus versus error correction window studios, availability plus versus management cost plus Kafka.
That lays out the choices very clearly. So let's get really practical now. Walk us through an implementation example. A video source comes in. What happens step by step to get it to the viewer through this whole system without any hiccups?
Okay, let's trace that path. Imagine a live camera feed hitting the system. The quick walkthrough. It hits both clouds at once. Both encoded into tiny chunks in parallel. All metadata changes sync instantly between them. Both feed the chunks to multiple CDNs. Smart routers direct viewers to the best stream, and everything is monitored constantly for tiny drifts.
Right. Let's follow that flow in detail.
Step 1, source ingest. The raw video feed doesn't just go to one cloud. It hits redundant ingest endpoints simultaneously in both AWS and Azure, usually geographically close ones. This ensures that even if, say, the Azure ingest point has a temporary blip, AWS is still getting the feed cleanly, and vice versa.
Dual ingest for immediate redundancy. Check.
Step 2, parallel encoding. As soon as the feed arrives, both clouds fire up their encoders. They run in parallel, doing the exact same job. They use those short GOPs, chunked transfer encoding to send pieces out as they're ready, and aggressive segment publishing using CMAF-LO, or maybe WebRTC. Both are racing to get tiny, playable chunks ready, ASAP.
Encoding happens everywhere at once.
Yeah. Step 3, metadata sync. This is happening constantly in the background, but it's critical. Any change, stream resolution, add marker insertion, configuration update triggers a CDC event. That event gets fired onto the shared message bus, maybe Kafka, or using the global database replication itself.
Hmm.
Within milliseconds, both the AWS side and the Azure side know about the change and update their own contexts accordingly. They stay perfectly aligned.
The magic whiteboard gets updated instantly. Okay.
Step 4, packaging and delivery. Once encoded and packaged into those small segments, both the AWS pipeline and the Azure pipeline relay their segments to global CDN origin points. Often, you'd use origins from both cloud providers, plus potentially a third-party CDN, giving you multiple delivery paths.
So segments are available from multiple clouds via multiple CDNs.
Exactly.
Hmm.
Which leads to step 5, session steerer and smart routing. This is where the intelligence sits for the viewer experience. A dedicated service, a session steerer, or a smart DNS system monitors the health and latency of all the delivery paths, AWS CDN1, Azure CDN2, etc. When a viewer starts watching, the steerer directs their player to the currently optimal path. If that path degrades, it can reroute the player midstream to a healthier path, often without the viewer noticing.
Clever routing switches viewers seamlessly. And finally,
Step 6, active monitoring. Underpinning everything is constant, granular monitoring. Automated probes check end-to-end latency, segment availability, and importantly, state consistency between the clouds. They're looking for drift, even sub-second drift. Health checks are constantly running, feeding data back into the routing system and triggering automated failover actions if thresholds are breached. It's a continuous feedback loop.
wow, that's quite the orchestration. So key implementation steps are:
I'd boil it down to 1, dual ingested encoding from the start. 2, real-time state updates via CDC, keeping everything in lockstep. 3, intelligent delivery using smart routing across multiple CDNs. And 4, that constant feedback loop from monitoring driving resilience.
It really sounds like an incredibly fine-tuned machine. But even the best machines break down sometimes. In a system this distributed, this real-time troubleshooting must be a nightmare when things do go wrong. What are the warning signs, the telltale signs of trouble, and how do you even begin to fix them when time is so critical?
Yeah, troubleshooting here is definitely not for the faint of heart. It requires a deep understanding of the whole stack, from network to codec to database replication. The quick version of what to look for: weird intermittent state differences between the clouds, video segments not lining up quite right, or sudden increases in player buffering. For fixing it, think time sync checks, auditing your data queues, using methodical debugging like the 5 whys, and deploying probes that act like real users.
Okay, tell us more about those trouble signs.
Right. What you really need to watch for are subtle things, often intermittent. 1, intermittent state drift. This is that split brain problem. Maybe for a few seconds, AWS thinks the stream is configured one way, and Azure thinks it's slightly different. It might resolve itself, but it indicates an underlying sync issue. 2, segment misalignments. Viewers might report seeing repeated frames or jumps or audio-video sync issues. This often points back to problems with timecode accuracy or clock drift between the encoding nodes in the different clouds. 3, surges and rebuffering. If suddenly lots of viewers start experiencing buffering, especially if it correlates with one cloud or CDN path, that's a strong indicator of a network bottleneck or a CDN performance issue along that specific path.
Okay, so those are the symptoms. How do you diagnose the cause?
First things first, always validate time synchronization. Check NTP status across every single node involved in processing and state management in both clouds. Even tiny clock drifts wreck these systems. It's the most common culprit for weird alignment issues. Second, audit your CDC event queues. Are messages getting delayed? Are there any drops? Is the replication lag higher than expected? The state database and its replication mechanism are critical, so check their health and performance closely.
Time sync, check. CDC queues, check. What else?
Use structured problem solving. The 5 whys technique is great here. Keep asking why to get to the root cause. So why are viewers seeing segment misalignment? Because segments from Azure are arriving later than segments from AWS. Why? There's higher latency on the Azure to CDN path. Why? Network congestion on a specific peering link used by Azure. Why? And so on. It stops you from just fixing symptoms.
Digging deeper with the 5 whys. Good one.
And critically, deploy synthetic edge client probes. These are like automated test users placed around the world. They constantly request streams via different paths and measure not just the end-to-end video latency, but also how long it takes for a state change, like a metadata update, to propagate and be reflected in the stream they receive. This gives you invaluable real-world performance and consistency data.
Probes give you the outside-in view. Smart.
Mhm.
Any best practices for preventing issues in the first place?
Definitely. Two big ones. Always use canary sessions or canary deployments. Before you roll out a global config change, test it on a small percentage of streams or users first to make sure it doesn't break anything unexpectedly. And build retry logic and idempotency into your synchronization mechanisms. It means if a state update message fails to send, the system automatically retries. And if it accidentally sends the same update twice, the receiving end handles it gracefully without causing errors. Makes the sync much more robust to transient network issues.
Canary tests and robust sync logic. Got it. So key troubleshooting points are?
Okay. 1. Monitor for drift and misalignment. Those are your key warning signs. 2. Validate time sync rigorously and first. 3. Audit CDC queues for lags or drops. 4. Use 5 whys and synthetic probes for deep diagnosis. And 5. Employ best practices like canaries, retries, and idempotency in your design.
This has been incredibly insightful. We've really covered a huge amount of ground, from the high-level concept down to the nitty-gritty of implementation and troubleshooting.
Yeah.
The level of expertise needed to build and run these systems is just staggering.
It really is. Achieving this sub 100 millisecond active multi-cloud video pipeline with perfect state synchronization, it's genuinely at the cutting edge. It demands deep knowledge of distributed systems theory, real-time data capture, state management under pressure, plus relentless tuning of networks and codecs. It's definitely a step beyond your standard cloud broadcast setup, and certainly something that showcases advanced skills in an interview context. And maybe a final thought to leave you with. We've talked about this intense level of real-time, resilient, multi-cloud architecture purely for video, but think about what the principles we've discussed, the instant state sync, the active resilience, the low latency could mean for other industries. What about massive IoT data processing where sensor readings need immediate, reliable handling? Or high-frequency financial trading where milliseconds mean millions? How might these concepts of distributed state, CDC, and active design apply in those fields? What new possibilities does this kind of engineering unlock beyond just video streaming? Something to ponder. That's all for this topic. Stay tuned for the next DevOps Cloud interview question.